So the first thing we're going to do today is we're going to talk about rationalizing denominators. Rationalizing means to make something into a rational number. And the convention in math is we do not want a radical sign in the denominator of a fraction. And I think the reason usually given is something around the lines that, well, a fraction, we're dividing the denominator is the number of parts we're dividing something into. It's like the fraction 3/4 means we divided something into 4 parts and we're looking at 3 of those 4 parts. Like 3/4 of an inch is, right, an inch is divided into fourths and our measurement is 3 of those fourths. And so the thought is, doesn't make sense to divide something into the square root of 3 parts or into pi parts or into the square root of 11 parts. Those things don't make sense. And so we don't want a radical sign in our denominator. This is not something that's going to be super important for us in this class. We are going to do a couple of problems with it today. A problem might show up on a quiz or an exam. But it won't be a huge part at all. It becomes important because when you go on to other classes, the expectation is that your denominators will be rationalized. So definitely if you go on and take college algebra or college algebra and trig, and you will eventually get to the point where you might have a radical sign in your denominator, you'd want to rationalize it. That's not going to happen a lot probably until that course, or courses like that elsewhere. But we want to be able to do it. And it's not that difficult to do in the grand scheme of things. It takes a little effort, but not too bad, in my opinion. So what we do is if we saw something like number 15 here, and we got an answer, we had done some arithmetic, we got an answer to a problem, and our answer is 15 over the square root of 6. What we should think to ourselves is, oh, there's a radical sign in my denominator. There's not supposed to be. How can I get rid of that radical sign? And so to get rid of it, what we do is we multiply the numerator and the denominator by whatever that radical is. So here we have the square root of 6. So we divide both the numerator, we multiply both the numerator and the denominator by the square root of 6. We multiply them both by it, not divide them both by it. And of course, that's because the square root of 6 over the square root of 6 is 1. We're just making like an equivalent fraction. And so we get 15 times the square root of 6 over 6, because the square root of 6 times the square root of 6 is the square root of 36. And the square root of 36 equals 6. And then we can simplify, take out a common factor of 3. 15 divided by 3 is 5. 6 divided by 3 is 2, and we get 5 square root of 6 divided by 2. This is as simplified as this problem can get. Some people want to go cancel crazy, and they want to think they can take this 2 and they can simplify this to be the square root of 3. That does not work. You cannot divide into a square root sign, into a radical sign. Now I say you cannot. Technically, you can do some stuff with perfect squares and it works because the way perfect squares work, but for our purposes, just don't. Make sure whatever is under the square root sign is as simplified as it can get, and then do simplification of whatever is outside of the square root sign. Sometimes you'll see something like option B here, where our answer is the square root of 3/5. How can we simplify this? Or how can we rationalize this denominator? Here, the first thing we want to do is we want to apply the quotient rule. And so what we're going to do to apply the quotient rule is we're going to rewrite this as the quotient of 2 square roots, the square root of 3 divided by the square root of 5. Now we clearly see that we have the square root of 5 in our denominator. We multiply numerator and denominator by the square root of 5. And we get the square root of 15 over the square root of 25. The square root of 25 is 5. So we have for our answer the square root of 15 divided by 5. And we again want to check that numerator. Could we simplify the square root of 15 at all? No, we can't. No perfect squares inside of 15. So this is as simplified as it gets. This is my correct answer, my only correct answer. Let's take a look at a couple of examples here, a couple of more that including one or two that are a little trickier. And this, and this, and this. All right, so hopefully you can see my whiteboard right now. Again, if you can't see the whiteboard for some reason, you can't see the screen right now, try logging out and logging back in again. If that doesn't help you, let me know and I will try unsharing and resharing because that sometimes works also. So we're going to take a look at some denominators to rationalize. So let's start with, I don't know, 30 over the square root of, let's just do the square root of 5, actually. That should be fun. So to rationalize this denominator, this is a pretty straightforward one. I multiply both the numerator and the denominator just by whatever my square root is. And so my numerator is going to become 30 times the square root of 5. My denominator is the square root of 25 then, because the square root of 5 times the square root of 5 is the square root of 25. So I have 30 square root of 5 over 5. And then I can simplify because 5 goes into 36 times and into itself once. And so my final answer is going to be 6 square root of 5. Sometimes we will have some that are a little trickier. And so here is one trickier one. So we have 20 over the square root of 20. In a problem like this, one thing we want to do, there's two approaches we can take. One thing we could do is we could simplify the square root in the denominator first. And that is usually, I think that usually that makes the process simpler. Now it turns out, because I did this problem this morning, it turns out I don't think it makes this one simpler. It makes it actually a few more steps in it, but I'm still going to do that. We could also just multiply both by the square root of 20, and I'm going to do that first. So even though we could simplify the square root of 20, we don't have to yet. We're going to have to at the end. So I could just multiply by the square root of 20 over the square root of 20. And so my numerator becomes 20 times the square root of 20. And my denominator becomes the square root of 400, because 20 times 20 is 400. So I get 20 times the square root of 20 over 20, because the square root of 400 is 20, of course. And then I can simplify. And my answer is the square root of 20, which I then need to simplify that, of course. The square root of 20 is the square root of 4 times 5, which is the square root of 4 times the square root of 5. And so I get at the very end 2 times the square root of 5. My other possibility for this problem is to start, make this a little bit smaller, I think, is to start by instead simplifying my square root. So I could start by saying, oh, I can simplify the square root of 20. The square root of 20 is the square root of 4 times the square root of 5. So that's 20 over 2 times the square root of 5. And then, so I'm going to then get 10 over the square root of 5. And then I can multiply Whoops. Sorry about that. Then I can multiply numerator and denominator by the square root of 5. That's supposed to be a 5 in both places. So I get 10 square root of 5 over the square root of 25. That is 10 square root of 5 over 5. Again, I simplify, and I get 2 square root of 5. So it doesn't matter which approach you take, they will both roads lead to the same answer. Sometimes it is much simpler to simplify the denominator first. Sometimes that's especially true if it's a number you really don't want to multiply. Like 20 is not a bad number to multiply. But if you had something like the square root of 98, for example, that might be something that you want to simplify first rather than multiply the numerator by 98 by 98. Nothing wrong with using the calculator, but we want to avoid using the calculator as much as we can just because it's so time consuming. Let's do another example. Again, I want to do kind of a trickier example sometimes. So let's do one that looks like, oh, I don't know. Let's do 5 square root of 6 over 2 square root of 7. Yeah, that'll work. That'll work just fine. So what I want to do here is I'm going to multiply both just by the square root of 7. This isn't super tricky. So my numerator becomes 5 times the square root of 42, because 6 times 7 is 42. My denominator becomes 2 times the square root of 49, because 7 times 7 is 49. And so then I'm going to get 5 over the square root of 42 divided by 2 times 7, which is 5 square root of 42 over 14. I can't simplify 5/14 at all. And the square root of 42, even though it looks like a number that should have a perfect square in it, 4 is not a factor, 9 is not a factor, 16 isn't a factor, and 25 certainly isn't a factor, so it really doesn't have a perfect square in it. We can't simplify the square root of 42 into anything that will make it any simpler than it is for this problem. So this becomes our final answer. This is usually the way you would write this. Sometimes you might see something like this written like 5/14 times the square root of 42. That's also acceptable. Like I would consider either of those correct. Yeah, either way. And then we'll do the last one. We'll do a fraction. Let's do one that has a nice, let's do 98. So I want to simplify this. I don't think 7 goes into 98. Actually, I think it does. So that could actually work. But we'll pretend I don't know that 7 goes into 98, or because I might be multiplying, dividing wrong in my head. So if we have a fraction like this, we can just simply break it up into the square root of the numerator divided by the square root of the denominator. 98 can be simplified. And 98 is the square root of 49 times 2. And the square root of 49 is 7. So I'll let me break this up. We'll do one more step here, actually. So the square root of 49 is 7. So I have 7 times the square root of 2. Now I'm going to multiply both sides by the square root of 2. And I'm going to get the square root of 14 over the square root of 7 times the square root of 4, which is the square root of 14 over 7 times 2, which is the square root of 14 over 14. And 14, again, doesn't have a perfect square as a factor, so we can't simplify that any. This becomes our final answer. Square root of 7/98 is the same as the square root of 14 over 14. I want to actually also show you how to check this on your calculator. So I should add that some calculators will keep square roots as square roots of certain fancy calculators. You should be aware that in most math classes at Iowa Lakes, those super fancy calculators aren't allowed. So like in finite math and statistics, the TI 89 isn't an allowable calculator. You have to use a TI 83 or a TI 84. In other classes, it's kind of at the instructor's discretion. Like I think Professor Strom lets people use it in calc, if I remember right. I'm looking at his syllabus, but in any event, we should be able to do it by hand like this anyway. But we can check our answer with the calculator. To check the answer, we want to do something like this. So we're going to approximate both of the square roots. We're going to approximate the square root of 7/98, and we're going to approximate the square root of 14 divided by 14. So I'm going to start with my original problem. So let's see if I can do this on here. So I'm going to type in 7/98, and then I'm going to take its square root, and that's about, according to my calculator, it's approximately 0.267. So this is approximately 0.267. Now I'm going to do the same thing over here. I'm going to take the square root of 14. I'm going to divide that by 14. And I get, again, approximately 0.267, luckily. And so what the approximation tells me is that I've done this correctly. If I hadn't done it correctly, they would not be the same value. Again, that decimal approximation cannot be your answer. If you're rationalizing a denominator, you're not going to have a decimal part in your answer. You just won't. You might get a natural number, though, as your answer. That's entirely possible. In fact, let's do one like that. Well, that'll be our last example. And I'm going to grab this one from your book so I don't strain myself trying to come up with one that will work like this. Maybe I'll grab one from your book. Maybe I'm lying to you, and I'm not going to grab one from your book. Well, that's no fun. We'll do it this way. So let's say I have the square root of 4 times the square root of 5 No, we aren't going to do. Am I going to do 5? Yes. You know what? We're going to just ignore this because the only way I can get this to come out is if I do this in the denominator too, and that just isn't going to help us at all. So yeah, you're going to end up with, unless it's a really simple problem with a radical sign in your answer. So this would equal, unsurprisingly, 4 if we did all that work. So yeah, so we'll stop there for this. And we will then, I'll stop and ask, do you have any questions about square roots right now? I should add, your textbook does mention a little bit going through other types of roots. besides square roots. There are cube roots, there are fourth roots, and so on. We aren't going to focus on those in this class, but they show up in other classes. They show up in finite, kind of depending on who teaches your finite class and what book they're using. They, of course, show up in classes like college algebra and college algebra and trig. So other types of roots also exist, of course. It's not just square roots. All right. So let's go back to sharing a fun PowerPoint. We will take a look at the next section. Looks good. Get over here so I can keep an eye on the chat. All right. And it's my pretty face again. First of all, we are not going to cover clock addition. That is not something we're going to talk about. You can scratch that off of your to-do list because we aren't doing that section. If you're an elementary education major, you should do that section. You can talk to me about it after class sometime. If you're a math major, you should do that section. You can talk to me about it after class sometime. To do clock addition justice, we would end up spending an hour just on that. And we don't have time for that in a 3-credit class. And it's not something that comes up a whole lot. Instead, what we're going to talk about.
I'm mostly seeing Ashlyn's webcam, not yours. I don't know if that's me.
So let me reshare my webcam. Can you see, Carson, the screen, the PowerPoint?
No, all I see is Ashlyn.
So I'm going to suggest you log out, log back in.
Okay.
As we're waiting, what we're going to talk about instead are things that are going to show up in other math classes as well as later on in this class, and learn about the real numbers. That's the first half of the chapter. Really, half of the chapter is clock addition. So there's not of the section. There's not a lot for us to cover in 5.5. It is a lot of vocabulary, and so I'll just warn you about that. It's vocabulary heavy, but not too bad. And most of it are things you've seen or heard before. So the first thing I want to talk about is the set of real numbers. We so far in this class have talked about natural numbers. And remember that natural numbers, we use the letter n to represent them. And in this textbook and in most textbooks, the natural numbers are 1, 2, 3, etc. 4, 5, 6, 7. The whole numbers don't have a standard letter that goes with them. Just varies from book to book, and they even talk about it. For our book and our purposes, the whole numbers are the natural numbers, except they also include a 0. The integers have a letter that goes with them. It's Z. And the integers are the natural numbers and 0 and their opposites. So -3, -2, -1, 0, 1, 2, 3, 4, 5, and -4, 5, 6, -7, -8, and so on and so forth. And then we talked about the rational numbers a couple days ago, a couple classes ago. And the rational numbers are numbers that could be written as a quotient of 2 integers. And your book uses the very typical format A over B. And then last class and the start of class today, we also talked about the irrational numbers. Irrational numbers include things like pi. And then many, not all, but many square roots are irrational. For example, the square root of any prime number is irrational. Square root of any prime number is irrational. So if you were ever asked to list an irrational number other than pi, a good answer would be to do something like just think of a prime number and stick it under a square root sign, because that is definitely an irrational number. Both of these together, the rational numbers, including the integers, the whole numbers, and the natural numbers, along with the irrational numbers, make up the set of real numbers. And real numbers also have a letter that goes with them. It's an R, and it usually has a double bar on the edge here, or sometimes it's just in bold. So these are our sets of numbers. And these are mostly the only numbers we're going to deal with in this class. Now, those of you who took Algebra 2 or something like Algebra 2 in high school, you also learned about numbers that aren't real. And the numbers that aren't real are called imaginary. And imaginary numbers are basically square roots of negative numbers, like the square root of -1, which we even give a special letter to indicate it is imaginary. We aren't going to worry about imaginary numbers. In chapter 6, we're doing quadratic equations, and so I don't think even then imaginary numbers show up. If I remember right. Again, if you go on, take college algebra and trig, you'll definitely have a little work with imaginary numbers, but not a lot. Most of the math courses you take as your general ed math courses focus on the real numbers. Finite math does, stats does, this class does. So the real numbers are either rational or irrational. There are no numbers other than rational numbers or irrational numbers that are real. And the other thing is that these make up subsets. So like the natural numbers are a proper subset of the integers. The integers are a proper subset of the rational numbers. The rational numbers are a proper subset of the real numbers. And because n is a subset of z and z is a subset of q and q is a subset of r, there's a property that tells us that this means, as the chart shows us, that the natural numbers are a subset of R. They're part of the real numbers. So all natural numbers are whole numbers. All whole numbers are integers. All integers are rational numbers. And all rational numbers are real numbers. Also, all irrational numbers are also real numbers. So you might be asked to classify numbers as what sets are they part of. So here's one example of that. We're being asked to list the numbers in the set that are natural numbers, whole numbers, integers, rational numbers, irrational numbers, or real numbers. So let's do that. Sometimes they're going to try to trick you. This is one of those times. You might look at this list and say, I don't see any natural numbers, but there is one. The square root of 81 is a natural number because the square root of 81 is 9. And 9 is a natural number. Whole numbers. Well, every natural number is a whole number. So the square root of 81 must be a whole number. And then our other whole number in this list is 0. Integers. Every whole number is also an integer. So we have the square root of 81. We have 0. Then our other integer here is -7. Rational numbers. All integers are rational numbers. So we have the square root of 81. We have 0. We have -7. And then we have every number that could be written as the quotient of two integers. So -3/4 is definitely written in that format. We learned a couple classes ago that 0.6 repeating is actually 2/3. So any repeating decimal can be written as the quotient of two integers. So all repeating decimals are rational numbers. And finally, 7 3/10 is also a rational number because 7 3/10, we could write that as the quotient of two integers. That is 73/10. And then the irrational numbers are the numbers that are literally not rational. There are two of them that aren't on our list of rational numbers. So that would be the square root of 5 and pi. And then finally, the real numbers. All of the items in the list are real numbers. So we have classified this set of numbers as to what sets they belong to. What are they elements of? So the square root of 81, for example, is an element of n. It's an element of the whole numbers. It's an element of z. It's an element of q. And it's an element of r. I should add, sometimes when we talk about real numbers in math, and I certainly do this as well, math teachers will often just refer to these as the reals rather than the real numbers, just because we use that. I think we use real numbers so often in math. Saying reals is a time saver. And again, as you go forward in other classes, you will use different types of these numbers, and sometimes you will use only certain types. In finite math, for example, there are times when for an answer to make sense, it can only be a natural number. In other words, the answer, quote unquote, that you get might include negatives, but no, it has to be a natural number and it can't include a fraction. One of the homework questions I gave in finite this fall, for example, was asking about a business question. How many pairs of jeans would a certain company have to sell to make a profit of $1,000 or something like that? And the answer, quote unquote, that the calculator gave was something like they would have to sell 335.2 pairs of jeans. Of course, the problem with that is that you can't sell 2/10 of a pair of jeans. And so, and if you sold only 335, if you rounded the way we would normally round, you wouldn't make that profit. You'd be like, a couple cents short. So, or more than a couple cents, actually, you'd be a couple dollars short. So you have to go to say you have to sell 336 jeans. So we have to, in some cases, even though the answer might be a rational number, the correct answer, we have to express it as a natural number. And here again is the textbook going through what I just went through, describing how that works. Any questions so far? Oh, good. I'm glad. At the problem solved, not that there are no questions. I always like questions. Properties of the real numbers. Some of these properties you've seen before, probably, and some you may not have. Some are going to be important going forward, and some are just things that you, I think, should know. One thing I want to point out is that most of these properties are very specific, and you should be very specific when referring to them. Many of the properties we're going to talk about today have two versions, one for addition and one for multiplication. When you're asked to name a property, and you will be, you need to be specific. It's not okay to say the blah, blah, blah property if there's an addition version and a multiplication version. You have to say the blah, blah, blah property of multiplication, or the blah, blah, blah property of addition. So the first two properties we're going to talk about are the closure properties of addition and multiplication. These for us right now are pretty straightforward. They aren't super important for us to know. They become more important in other classes. So first, for addition, the closure property of addition tells us that if we add any two real numbers together, our answer is going to be a real number. So if I add 2 plus 7, I know my answer will be a real number. If I add -3 plus pi, my answer is going to be a real number. I could never add two real numbers together and get an imaginary number as my answer. It just won't happen. The closure property of multiplication is the same idea, except for multiplication. The product of any two real numbers is a real number. So -3 times -8 is going to be a real number. Pi times the square root of 73 is going to be a real number. 0 plus 20 is going to be a real number. We say sometimes that the real numbers are closed in respect to addition, and that the real numbers are closed in respect to multiplication. Some number sets aren't closed in some of these ways. for certain types of numbers. So that's especially true for things like division or subtraction. If we subtract a natural number from a natural number, we might get an integer. We won't always get a natural number, for example. And again, the closure property isn't super important for us in this class, but they show up again and they become more important in some higher math classes like college algebra and trig, but really even beyond that. More important for us, and one that you're probably familiar with, are the commutative properties. There's the commutative property of addition and the commutative property of multiplication. But these both involve order. The order doesn't matter if we're adding numbers together. That's the commutative property of addition. 12 plus 73 is the same as 73 plus 12. The commutative property of multiplication, order doesn't matter when we multiply factors together. 1/3 times 7 is the same as 7 times 1/3. And you see examples of all of these properties on the screen. For the commutative property, think about commute as the root word, and think about a commute, a drive somewhere. If you have a commute to work of, say, 10 miles, it's the same distance when you leave home to go to work as it is from when you leave work to go home. The distance doesn't change, even though the point you started from changes, because you're going from one destination to the other. It's the same thing for numbers when we add or subtract. The order, when we add, sorry, not add or subtract, when we add or multiply, it does make a difference in subtraction. But when we add or multiply numbers, real numbers, the order doesn't matter. We can multiply or add in any order we want. Related to the commutative property is the associative property. And again, there are two associative properties, one for addition and one for multiplication. For addition, it means that we can group add-ins. Add-ins are the numbers we're adding. We can group add-ins together however we want. And when I say group them, we don't change their order. We change the order of grouping symbols like parentheses. And so you see that in the example on the right-hand side. In parentheses, 7 plus 2 plus 5 is the same as 7 plus, in parentheses, 2 plus 5. We can move parentheses and it doesn't change the answer. Notice that none of the other numbers have been rearranged. If we're rearranging a number, we're using the commutative property. If we're rearranging parentheses, we're using the associative property. So associating means grouping, like the people you associate with are the people you hang out with. And so with numbers, when we associate numbers together, we group them with parentheses. Think of it as giving them a hug to keep them close. There are your arms hugging 7 and 2 together, so they are associating with one another. And then you get mad and you instead hug 2 and 5 together, so they are associating with each other. In either case, we get the same answer, and the order of the numbers doesn't change. Associative property multiplication, same idea, except for multiplication. The order of the factors doesn't, or the order, how we group the factors, where we put the parentheses doesn't affect the answer. And again, notice here, our factors are in the same order. 7, 2, 5, 7, 2, 5. We haven't changed the order of factors. What we've done is we moved the parentheses. And remember, we do what's in parentheses first. So 7 times 2 is 14. 14 times 5 is 70. We do what's in parentheses first. So 7 times 10 is 70. We do this associative property commonly when we're doing mental math in our heads. If you're like me and don't have your 14 times table memorized, you probably don't want to multiply 14 times 5. On the other hand, multiplying 7 times 10 is a pretty easy multiplication that most people can do. So, associative property, how we group something doesn't affect the outcome. But again, For the associative property, we're keeping the digits in the same order. A common mistake that people make on the homework, on quizzes, on exams, is to confuse the commutative property and the associative property. The other common mistake they make is they don't give the entire name of the property. You have to say associative property of addition or associative property of multiplication. The next property that you almost certainly learned in high school is the distributive property, and the full name there is the distributive property of multiplication over addition. For this particular property, even though normally I'm telling you, you have to be very specific, I'm going to say you don't have to be, because this is the only distributive property we're going to be talking about. And so you can, if you want, refer to this property in this class as just the distributive property. Please do not go on to college algebra and tell your instructor, Mr. Lund said we could just call it the distributive property. Because I will find you and I will throw things at you. So it's okay to call it the distributive property in this class, but in other classes, call it what they tell you to call it. Now, technically, there is also the distributive property of multiplication over subtraction. It works the exact same way, and normally they don't separate the two because all subtraction is the opposite of addition. And so, but like if I, instead of a plus sign here on all of these, had a minus sign, we would still get the same answer. I mean, it would still work out. Like, it would be a different answer, but it would still work out using the distributive property. And so, like, I think in math for elementary teachers, we actually do distinguish between distributive property over addition and the property over subtraction, but we don't have to in this class. And again, the distributive property is one that we use a lot. It also works backwards, and the backwards one actually does have a different name that I don't remember right now. But we could also say that B plus C times A equals B times A plus C times A. So it can also go in this order. And it can also go, obviously this equal sign means it works either way. So you'll also have problems sometimes where you might start with this. In fact, you will have problems sometimes where you're going to start with this. And from this, you're going to say, oh, this is the same as 7 times 4 plus the square root of 3. So remember, that equal sign means it goes either way. The next two properties are the identity properties. The identity property of addition, I really dislike how your book describes these. Your book's definition for the identity property of addition is that 0 can be deleted from a sum. I don't particularly think delete is a good math term, but that's just me. It makes more sense to me simply to say that 0 added to any number equals that number, or something like that. And that's what it means. You see the two versions of it here. If I have some number A, any real number, and I add 0 to it, my answer is going to be A. If I start with 0 and add some real number A to it, my answer is going to be A. We say that 0 is the identity property of addition, or we say that 0 is the identity element of addition. We say that 0 is the identity element of addition. Now, it's completely reasonable for you to think to yourself, why in heaven's name do we need to know what the identity property is? I know that anything plus 0 is that number. I've known that since I was a first grader. And frankly, it's not super important for what we do in this course, but it becomes important for things in other math courses. If you go on and take finite math as one of your other math classes, for example, we'll talk about identities of matrices, which are not a single number, but are themselves a matrix and have particular properties that are important there. So the identity properties, it's not that it's super important that you know them right now, But it's important that we start working on understanding how they are part of the rich tapestry of mathematics. Second identity property is the property of multiplication. And again, your book bizarrely says this means one can be deleted from a product, which is one of several things in your book that makes me sigh, but I don't get to choose the book for this class. Again, it simply means that any number times 1 is that number, or 1 times any number is that number. And we say that 1 is the identity element of multiplication, or the multiplicative identity. And again, we use this property all the time in algebra. You use it all the time in high school algebra. When we figure out something, we say, oh, the answer is 1x, but we just write x. Or we say, oh, the answer is, negative 1y, but we just write negative y. What we're doing in a case like that is we're making use of the identity property. And they've shown us that a little bit here with numbers instead of with variables. One reason these identity properties are important is because of the final 2 properties we're going to talk about of the real numbers today. And those are the inverse properties. Again, there's an inverse property of addition, and there's an inverse property of multiplication. For the inverse property of addition, the sum of any real number and its additive inverse gives 0. And as we've seen, 0 is the additive identity, or the identity element of addition. And so if you had, if you start with negative 1/3, negative 1/3 plus positive 1/3 is 0. If you started with the square root of 10, the square root of 10 plus the negative of the square root of 10 is 0. Any number plus its additive inverse is 0. The additive inverse of a number is simply that number with an opposite sign. So if it was positive, it becomes negative. If it was negative, it becomes positive. And the final of our properties we're going to cover is the inverse property of multiplication, which is that the product of a non-zero real number and its multiplicative inverse gives us 1, which is the multiplicative identity, or the identity element of multiplication. And so you see a couple of examples here. The multiplicative inverse of the square root of 3 is 1 over the square root of 3. The multiplicative inverse of 1 over pi is pi. This is what you do when you divide fractions. You were taught probably back in elementary school that to divide a fraction by a fraction, you're supposed to invert and multiply, or take the reciprocal and multiply, or flip and multiply. In all of those cases, what you're doing is you're finding the multiplicative inverse. So the multiplicative inverse of 3/4 is 4/3, because 3/4 times 4/3 equals 1. And some math instructors get super annoyed when someone says something like, we're going to flip and multiply, or take the reciprocal and multiply, and they levitate off the ground. And I understand why they levitate off the ground, but at the same time, having taught 5th grade, you don't want to teach 5th graders multiplicative inverses, because your head's going to explode, or you're going to go to jail, one or the other. Again, any whole number, its multiplicative inverse is just, whoops, not equals, Carl. Any whole number, its multiplicative inverse is going to be that number underneath a 1. Any fraction, its multiplicative inverse is going to be swapping the numerator and the denominator. And again, why this is important, it's important because if we multiply something by the inverse, that's the same as dividing it. In other words, dividing something by pi is the same as multiplying something by 1 over pi. That's important because there are some types of math where we can't divide. Division isn't defined for it. And in fact, that's kind of true for fractions. That's why we invert and multiply for fractions, because division really isn't defined as such in a good way for fractions either. So there's a couple of things you're going to have to be able to do. I am not going to ask you to regurgitate out a definition of a property for me. What you're going to have to be able to do, though, is potentially one of three things. One is you might see an example of a property and you'll be asked to name it. So our examples here, we would have the first one. This is the commutative property of multiplication. And it's the commutative property because we swapped the order. Instead of the square root of 3 times 7, we have 7 times the square root of 3. And they equal each other. Because order doesn't matter, they still equal each other. That's the commutative property. We're multiplying, so it's of multiplication. Associative property. Notice here, 4 plus 7 plus 6 equals 4 plus 7 plus 6. The order of the digits hasn't changed. The only thing that has changed is where the parentheses are. That's the associative property of addition. Here we have the distributive property, and again, you can just say the distributive property of multiplication over addition. 2 times 3 is 6. 2 times the square root of 5 is 2 square root of 5. And then finally, the inverse property of addition, as an example, finally, 17 plus negative 17 equals 0. So you might be given an illustration of a property and asked to name the property. You might be given a property and asked to illustrate it. And so you might be told commutative property of addition. And so you would write 2 plus 4 equals 4 plus 2. There we have an example of the commutative property of addition. Please don't write 1 plus 1 equals 1 plus 1. And say, oh, I switched the ones around. That doesn't work. It is a nice try, but it doesn't work. Okay, use different numbers. Don't repeat. So you might be asked to give an example. And then the other thing you might be asked to do is to have something that is partially worked out. So 3 times 2 times 5 equals. So you might be given this and then said something like, insert parentheses to illustrate the associative property of multiplication. And so you would then, I'll use different ink here, say, well, parentheses are at the end. I'm going to move them so they're at the beginning. So I've now illustrated the associative property of multiplication. And we could actually go on and illustrate and say, well, that's going to be 3 times 10 equals 6 times 5. And so we have 30 equals 30. So you might be asked to do one of those 3 things. Name a property that's illustrated, or illustrate a property when given its name, or complete a partially completed property. Any questions about properties? Okie dokie. Again, I kept the clock arithmetic stuff in the PowerPoint from your textbook in case you're interested. So it's there, but you are not responsible for any of it. It's not going to show up even as extra credit. It will, symmetry and clock arithmetic, especially clock arithmetic, are not going to show up in this class at all. Before we go on and talk about exponents, I do want to talk about your midterm exam. Your midterm exam is going to be a week from today, and here's how it's going to work. It is going to be a take-home exam. We are not doing it in class. You do not have to have it proctored. We will not have class 1 week from today. So if you want, you can take class time to complete the exam. You do not have to take class time to complete the exam. The exam will open for you at midnight on October 8th, and it will close. It'll have to be submitted by 11:59 p.m. on October 8th. So you can do it anytime you want over that 24-hour period. If you know that you have an unavoidable absence on October 8th, let me know and I will let you take it the day before. There will be different versions of the exam for different students. It will be randomly assigned. They will all cover the same sorts of materials. The questions will all be at roughly the same difficulty level. You are free to use your book because it is a take-home exam. You can use any notes you've taken. You can use your calculator. Please do not work together on the exam. Please do not try to get help from anyone. Do not ask Megan or some other tutor or some other instructor, hey, how do you do this? Even if it's not the exam question. If you're just like, oh, wait, I forgot how to rationalize a denominator. And you go to someone, can you explain how to rationalize a denominator to me? Please don't do that. Because of doing it virtually, I'm trying this approach rather than having a proctored section for us. Please respect that by not cheating on the exam. Be aware, the final exam is proctored. You will either do it in honor lock or you will do it in class during our scheduled final exam time during final exam week. So the final exam will be proctored, but this, your midterm exam, will be a take-home exam. There will be a study guide still. The study guide will go up sometime this weekend. I'm working on it now, in fact, or not now, because I'm teaching you. But I was working on it earlier today. And it's going to be a really generic study guide because, again, it's take home and it's open book. You have your book to use. But on the study guide, I will talk about the types of problems that will be on there, as well as sample problems from your textbook that I would encourage you to work to prepare or to see what sorts of problems you can expect. And so, in fact, I think I have that up right now. Yes. So here right now is the chapter 1 part. It's going to cover chapters 1, 2, 4, and most of 5. It's going to cover what we cover in chapter 5 today. And there's going to be some topics from chapter 5 on Tuesday of next week that are going to be on it as well. And they won't make up a large part of the exam, but there will be a question or two from the stuff next week. You can definitely expect questions on things like irrational numbers to be on the exam. You can definitely expect to have to do prime factorization and other things we've done recently. But working back a little bit, I know the study guide can help or maybe refresh some things so you can get prepared for it. I don't have the exams written yet, so I can't answer questions like how many questions are there, what format is it going to be, are we going to put our answers in Canvas or are we going to write them and take pictures? I honestly don't know those answers yet. I'm trying to figure out a way that is reasonable for you and is reasonable for me, and is reasonable that Canvas isn't going to blow up. So I will let you know that once I figure it out. In fact, we will talk about that in class on Tuesday of next week. And I may post an announcement saying once I know things like how many questions or what format will it be. I would guess, this is just a guess right now, I would guess that at least some questions will be multiple choice. And I say that because your final exam is going to be mostly multiple choice because it just is for this class. And so since the final is multiple choice, it makes sense to me that the midterm would be multiple choice. I can also say pretty confidently that although parts of it will probably be multiple choice, it will not be entirely multiple choice. And I can also say pretty confident you will have an opportunity for extra credit. What I typically do is say every question on an exam is worth 4 points and the exam is worth 100 points. So 25 questions times 4 points each is 100 points. But what I will typically do is instead of having 25 questions, we'll have 27 or 28 questions. So you could earn 108 points out of 100 if you got everything right. Or you could miss 2 questions and still get things right. Any questions about any of that so far that comes to mind right away? All right, we then are going to finish today by talking about exponents. And so this is chapter 5, section 6, exponents and scientific notation. You've dealt with exponents before. We've dealt with them before in this class. And they get sort of formally introduced in more detail in chapter 5. Because this is also where we're talking about scientific notation. And you may or may not have had exposure to scientific notation before. It just kind of depends on what your school's math curricula were or what their science curricula, whether it was included or not. We're going to talk about scientific notation specifically more on Tuesday. Today, we're going to mostly talk about bullet point 1 here, the properties of exponents. So I do want to point out, in case I forget to on Tuesday, because I do forget this sometimes, your textbook uses the phrase decimal notation to refer to how we normally write numbers. Oftentimes, other textbooks use standard notation instead. But your textbook, and one of the several things that it likes to be unique, refers to that as decimal notation. So in past classes, you may have had that referred to as standard notation. Properties of exponents. Remember that the number we are raising to a power is called the base, and the power is called the exponent or the power. If we're multiplying exponential expressions that have the same base, and so for example, b to the power of m is an exponential expression. B to the power of n is an exponential expression. 9 to the 6th, 9 to the 12th, 3 to the 4th, 5 to the 12th, 9 to the 5th, all of those are examples of exponential expressions. When you're multiplying exponential expressions that have the exact same base, you add the exponents, and the base stays the same. So if we take 9 to the 6th times 9 to the 12th, that is 9 to the 6 plus 12, which is 9 to the 18th. This is also true for variables. If we had x cubed, that's a 3, times x to the 5th, that would be x to the 3 plus 5, which is x to the 8th. As long as the base is the same, when we are multiplying bases together, we add their exponents. One problem that sometimes shows up that often confuses people is a problem like this. So here we have 4 times 4 to the 9th. And a problem that is similar to this, I think, shows up in the final exam. And every year, every semester, people miss it. And a common mistake is they think that because there's no exponent shown here, this must be 0. But of course, 4 by itself is really 4 to the 1st power. So 4 times 4 to the 9th, that would be the same as 4 to the 1 plus 9, which would be 4 to the 10th. Similarly, if I just have, this is pretty straightforward. This also illustrates it. 3 times 3 would be 3 squared. There's also so that's the product rule for exponents. The power rule for exponents is if we are taking an exponential expression like 3 to the 4th and we're raising it to a power. So like on the right-hand side there, you see we're taking 3 to the 4th and we're raising it to the 5th. In a case like that, we multiply the exponents. The base stays the same still. The base always stays the same for these properties. So 3 to the 4 times 5, that's 3 to the 20th. 5 cubed to the 8th power, that would be 5 to the 3 times 8. That would be 5 to the 24th. People often get these two mixed up. because they think, oh, we're multiplying exponential expressions, so we must be multiplying the exponents. But that's not true. If you're multiplying exponential expressions, you are adding the exponents, assuming you have the same base. And then there's the quotient rule. The quotient rule is related to the product rule. If you're dividing exponential expressions, and again, they have to have the same base, we subtract. We subtract the exponent in the denominator from the exponent in the numerator. So 5 to the 12th divided by 5 to the 4th is 5 to the 12 minus 4. That's 5 to the 8th. 9 to the 40th divided by 9 to the 5th is 9 to the 40 minus 5. That's 9 to the 35th. Again, this is a problem that sometimes trips people up. If we had something like 6 to the 10th divided by 6, that's going to be 6 to the 10 minus 1, or 6 to the 9th. If we had, again, this is the quotient rule again, if we had 4 to the 7th divided by 4 to the 7th, that would be 4 to the 7 minus 7, 4 to the 0, which is 1. And of course, anything divided by itself other than 0 is 1. And these rules, again, also all apply to exponents. If I had x squared raised to the 14th power, that would be x to the 28th. We talked about the zero exponent rule earlier in the course when we were talking about expanded form in chapter 4. If b is any real number other than 0, b to the 0 equals 1. Remember, 0 to the 0 is undefined. So we have some examples of this. Let me say that again. 0 to the 0, undefined. Anything else? 12 to the 0 is 1. Negative 10,000 to the 0 is 1. 3/8 to the 0 is 1. Anything other than 0 to the 0 power will always equal 1. And so we see examples here. 7 to the 0 power, 1. Pi to the 0 power, 1. Now they're going to try to trick you. And they're going to try to trick you with negative signs. This is the same way they try to trick you when we're squaring things, as we talked about earlier in, earlier in this chapter. Think about where the negative sign is. If it's inside parentheses, like it is here, this means we're taking negative 5 to the 0 power. Negative 5 to the 0 power is definitely 1. In choice D down here, we're not taking negative 5 to the 0 power. We're taking 5 to the 0 power, and then we're multiplying our answer by negative 1, or we're finding the additive inverse of our answer. So this is going to be 5 to the 0, that's 1, and then that negative, that becomes negative 1. And that's because the minus sign is not in parentheses next to the number. So again, this is negative 5. This does not represent negative 5 in a problem like this. This is the opposite of 5. Now, the issue with that is that opposite means we multiply it by 1. And in this problem, remember our friend PEMDAS from earlier this chapter. We do exponents before we multiply. So 5 to the 0 comes first, and then we multiply by 1. So watch your parentheses here, because they will try to trick you. And then the negative exponent rule, which is also sometimes a little bit troublesome. basically, remember about a half hour ago, I said, we don't want there to be, or an hour ago, I said, we don't want there to be a radical sign in the denominator. We just don't like it in math. We also don't like negative exponents in math. For an answer to be simplified, exponents, if they exist, should always be positive. We do not want a negative exponent as our final answer. And so we have then the negative exponent rule, which is that if b is any real number other than 0, and if m is a natural number, then b to the negative m is the same as 1 over b to the power of m. It is also true that 1 over b to the negative m is the same as b to the power of m. For example, if you were doing some work and you got your final answer as 3 to the negative 4, you would say that is actually 1 over 3 to the 4th power. And 3 to the 4th power is 81. So my answer here is going to be 1 over 81. If you had a variable and you had x to the negative 5, your answer would be 1 over x to the positive 5. Sometimes I've heard teachers explain this as the negative sign means the base is unhappy, right? If we're negative, we're unhappy. And it's unhappy because it doesn't like its position. And so if we move it downstairs to the denominator, it becomes happy. It changes its sign. It's no longer negative. Or if it starts in the denominator, like here, and we move it upstairs to the numerator, then it becomes happy. Its negative sign is lost. So a negative exponent means that that base wants to change places. If it's not in the denominator, it wants to be in the denominator. If it's not in the numerator, it wants to be in the numerator. It is unhappy where it is. Here's a couple or 3 more examples. So example A, we have 8 to the negative 2. That is 1 over 8 squared. That's 1 over 8 times 8, which is 1/64. 5 to the negative 3 is 1 over 5 cubed, which is 1 over 125. And 7 to the negative 1 is 1 over 7 to the first, which is just 1/7. Again, we could also have something in our denominator. We could have a number other than 1 also in our numerator. So if I had 3 over 4 to the negative 2, that's going to be the same as 3 times 4 squared, which is going to be 3 times 16, which is going to be 48. It's perfectly fine for you to use your calculator to check your answers here, but you also need to be able to do this without using the calculator. So let me just show you how to check your answers. It depends on your calculator. If you have like a TI-84, it is going to keep your exponents as exponents, which is very helpful in checking. But just with a regular scientific calculator, let's do 5 to the negative 3rd. That would be 5, exponent key, 3, make 3 negative, equal sign, and I get 0.008. I get a decimal version of my fraction. And so 0.008, then I'm just going to divide to check. Is 1 divided by 125 0.008? Yes, it is. So I can check my work using the calculator by first putting this into the calculator, and it's going to give me a decimal. Sometimes it'll be a decimal approximation, and sometimes it'll be an exact decimal answer. And then I do my work. I find my answer as a fraction. I put it in the calculator, and again, it's going to tell me what it approximately is. So the calculator can help you check but you have to be able to do it without using the calculator. Not that I'm going to be there to check that you have to do it, but I can kind of tell, because at some point I'm going to give a problem like this and somebody is going to put that their answer is 0.008. That was not an answer. I mean, it is, but I'll tell you that, actually, I'll tell you this right now in case I forget. If you're working with negative exponents like these, your answers will be fractions, or sometimes they might work out to be a natural number like 48. They will not include a decimal. Your answers should be written as fractions. Now, a more advanced calculator like the TI-84 also can handle this, and of course can show us our answer then as a fraction, which I can't keep you from doing, which is fine because you're going to use this in other math courses, specific calculator. But your answer for these exponent problems are either going to be typically a natural number, or an integer, I should say, like 48, or they're going to be a fraction like 1/64 or 1/125. Sometimes you're going to end up with a really large exponent, and then you can keep the exponent. So if I had 33 to the negative 15, your calculator probably can't handle that. You would write it as this, and you would keep it with an exponent. So for when you're doing problems like this, both in the homework set, that when it eventually shows up, but also for things like quizzes and exams, please read the instructions, because I will sometimes say something like, be sure to keep your answers as exponents. And if I say that, then I would want your answer to look like this. And if I said it for a problem like this, I would want your answer to look like this. This is if you're keeping them as exponents. If not, if that isn't stated, the expectation is that you're going to simplify as much as you reasonably can. No one expects you to reasonably simplify 33 to the negative 15. I mean and hateful, but not that mean and hateful. So let me see what it says in our calculator. Very appropriate. So when I put this in our calculator, I get 1.66836435 e negative 23, which is scientific notation, which is what we're going to talk about on Tuesday. Speaking of which, this is the last thing we'll cover today in our 2 minutes left. A positive exponent, when we're dealing with a power of 10, when 10 is our base, a positive exponent tells us how many zeros follow the 1. So 10 to the 9th is a 1 followed by 9 zeros. 10 to the 5th is a 1 followed by 5 zeros. 10, I'm not going to write all these out, but 10 to the 23rd would be a 1 and then 23 zeros. A negative exponent tells us how many places there are to the right of the decimal point. So like 10 to the negative 9 is 0.000, 000, 001. There are 9 places to the right of the decimal point. 10 to the negative 12, there would be 12 places to the right of the decimal point. So there would be, in that case, 11 zeros followed by a 1. When we're dealing with really large and really small numbers, these become kind of hard to work with once we get to 12, 15, 20, 23 zeros. Your calculator doesn't like it very much either. And that's when we go to scientific notation, which is what we're going to talk about on Tuesday. Any questions for me? All right, I am going to put the link in the chat. If you don't see the link, please email me. But there it goes. Again, if any questions pop up, please email them to me. Otherwise, have a good weekend, make good choices, and I will see you back in class on Tuesday. But until then, goodbye for now. Keep it real.